Let's work 4.107. Predict products and write balanced chemical equation for each of these reactions. In these reactions, we are given possible, well, not even possible reactions. We're just given things that can combine to react, and we are expected to predict products. Now, this could be a little bit challenging. I hope to give you a few hints as to which direction to go in if you're ever faced with a problem like this, but this is a problem of significant difficulty for you, I'm sure. Now, if I'm looking at a reaction such as this one, I'm trying to figure out what in the world could happen, I quickly try to think about the chemicals at play, their tendency to want to be oxidized or reduced, and what exactly could possibly occur here, okay? I'm just kind of use chemical intuition, I guess you could say. So I'm starting off with strontium solid, and I've got liquid bromine. Now I look at these two and I say, okay, what's my oxidation numbers? Well, 0 and 0, okay, because I've got elements in their uncombined form. And I start thinking about these elements a little bit to try to decide what do they like to do when they react and form different substances. And this guy's a metal, so it likes to lose electrons to become oxidized. And bromine, of course, on the other side of the periodic table, this is elemental bromine. It tends to like to gain an electron for each atom, and as a consequence become Br-1, or bromide, become reduced. Okay, so as something that kind of wants to be oxidized and something that sort of wants to be reduced, it stands to reason in my mind that what might happen is I carry out that type of reaction, okay? And I make a strontium +1 ion, or +2, and then a bromide -1. Now, if I look careful at strontium, it is in group 2 of the periodic table, which means it likes to form +2 ions, and each bromide likes to form -1. So if I'm going to balance this, I need to do SRBr2, balancing the charges. This is a 2+ cation. Each one of these is a -1 anion. I've balanced the charges to write my ionic compound. I've oxidized my strontium, which is what it likes to do. And I have, in fact, reduced my bromine, which is what it's generally happy with. If I look at balancing, I got one of these, one of those, two of those, two of those. Everything appears to be good. If I want to think about transfer of electrons here, remember we said when something is oxidized and it increases its oxidation number, so strontium in this case, it goes from 0 to +2. It had to what? Lose 2 electrons to make that happen. To go from 0 to +2, it lost its 2 electrons. And where did they go? Did not just disappear, bromine got them. There were 2 atoms of bromine. Each atom got 1 electron to make Br-1. The flow of electrons works out. Everybody's happy, okay? So that's kind of where I would go with that, all right? And obviously there's a lot of thinking involved, but the more familiar we get thinking about elements and their tendencies for reactions, the better you'll get, I think, at that type of thing. All right, B. We take this silver salt, silver oxide, Ag2O. And what we are going to do is we are going, or it's a solid, and we are going to heat it. That's what that triangle means, okay? Basically tells us that we are going to heat the heck out of this stuff. Now notice, there's only one reactant. There's nothing else there. And I know from my chemical experience, okay, that if you take a substance and you heat it enough, typically what happens is it decomposes into its component atoms, okay? So I'm already thinking that, okay, maybe this is a decomposition, and the fact I've got nothing else reacting, there's no other real possibility here, okay? So if this stuff is going to decompose, then we got to think about, okay, well, it's going to break down into its elements. Well, what is that? Well, silver is 1 silver solid. And then I guess I could make some oxygen. Oxygen comes packaged as O2, remember, as a gas in its elemental state. So I write silver in its elemental state, oxygen as O2 gas in its elemental state. When I'm writing the products of decomposition reactions, such as this, I always do so in the elements. Okay, if it's going to fully decompose down to elements, I write it as the elements in their elemental forms, and that's important. Okay. Now I need to balance this. To do that, I'd have to just put a 2 right here. Oh no, that's not going to work because my oxygen's out of whack. I have to have this 2 here. So before I do anything, I would need to put a 2 over here. Now my oxygen's balanced. It looks like I need to do a 4 here for my silver. Okay, so 2, 4, 1. And that works out. Okay, now in terms of redox chemistry, what occurs? Well, it looks like this silver is 0 oxidation state. This oxygen ends up being 0 because they're elements in their n-combined form. What were my oxidation numbers over here? Okay, well, oxygen generally, the rule is -2 for that, which makes each of my silvers +1. Right? So my silver goes from +1 to 0. It must have been reduced. Looks like my oxygen stays the same. Okay? All right, so moving on. Or no, I'm sorry, the oxygen doesn't stay the same. It goes from -2 to 0 because I make elemental oxygen over here on the right. So we increase the oxidation number there, okay? All right, so that one's been oxidized. Moving on to the last one. All right, manganese solid gets thrown into a beaker of aqueous copper nitrate. The copper oxidation state here appears to be +2, which is the typical case for copper, or atypical case for copper, because the nitrate, each one of the nitrate ions is -1. Manganese, the original redox state here is 0 because it's an element in its uncombined form. Now, I want to combine these things and think about what could possibly happen when I throw elemental manganese into this copper-based solution. Now, typically, what possibly happens in cases like this, and again, when I say cases like this, I'm specifically talking about you've got an aqueous solution of a metal salt, and you throw something different in there, a different element, okay? What possibly can happen in cases like this is the metals switch places. Right now, the manganese is in the reduced elemental form, and the copper is in the oxidized form, okay? But potentially, these two can switch places. They could flow electrons from one to the other, okay? Now, if that occurs in this particular case, in this particular reaction, what then can happen is I might form manganese nitrate aqueous. Here, manganese 2+, we'll say, and copper solid. So notice what happens. The copper was the ion, the +2. It ends up copper solid, the reduced form. The manganese was the elemental form, but as a result of this reaction, it ends up in the +2 oxidation state. It has been oxidized, the copper has been reduced. Now the problem is this is hypothetical at this point. We don't know whether or not this will occur or this will not occur. We need a mechanism or a way to predict whether it actually happens. Okay? Now, in this chapter, we have learned about something called the activity series of metals. Figure 4.24 of your textbook on page 186 shows this activity series of metals. What this is this is a listing or a table from top to bottom of a metal's strength as a reducing agent. As a reducing agent. Now, what does that mean chemically? What it means is it's a measure of the metal's tendency to want to be oxidized. Oxidized in the plus form, right? Things which are higher on this table are better reducing agents, which means they have a higher tendency to be oxidized than things that are lower on the table. So if you look at the bottom of the table, you'll see things like gold, silver, even copper is down that way. These are metals which are pretty noble metals. They don't really want to get oxidized in many cases. Now you can make them oxidize, but their natural tendency is against it, okay, relative to some of the other metals. So this is why the activity series is so crucial for problems like this. Because what we need to do is compare the two metals of interest in a reaction on that table.